My name is Brett Hesterberg. I'm the product manager at Google for our Cloud SQL service. I was here last year with a colleague to present on Cloud SQL. Did anyone in the room come to the Cloud SQL presentation last year at Percona Live? Or maybe more generally, we got one. And I think we had two hands there. More generally, did you come to Percona Live last year? Yeah. And no? Okay. We also gave a talk at Percona Live Amsterdam, so if you happen to find yourself in Europe later this year, we'll probably be doing a different talk on Cloud SQL there as well, and I'm sure we'll be back here again, so hopefully we'll see a few familiar faces next year. I'm going to cover a few things today. We'll talk about what Cloud SQL is as a managed service, and we'll talk a bit about differences between self-managing a database and a managed database service. I'll also demo Cloud SQL. I think that's the best way to really get to know the product, especially if you're not familiar with it. And then we'll talk a bit about performance scaling, how you scale infrastructure before getting into a little bit of database-specific tuning. I'm going to focus on our MySQL product today with some InnoDB tuning information. And then we'll talk about how you connect to Cloud SQL, get connected from clients before getting into some next steps. So before we jump in, let me just learn a little bit about the audience here, just by a quick show of hands. How many of you are developers? All right. How many are DBAs? And how about reluctant DBAs? No? Any managers in the room? We got one to two brave managers. All right, thanks. So let's start jumping in. Cloud SQL is a managed database service, and by that we mean Cloud SQL aims to offload the mundane tasks associated with database management. Make no mistake, it is not a DBA replacement. It doesn't do query optimization for you, for example, but I'll talk at fairly length about what we do in terms of management. Cloud SQL offers MySQL and, as of last month, Postgres as well. When I say we offer these databases, we're not offering MySQL compatibility or Postgres compatibility. We are offering as close to vanilla Community Edition MySQL as we can, and similarly as close to vanilla Postgres as we can. So what this means is if your application works with MySQL or it works with Postgres, it should work with Cloud SQL. Google has a fairly broad and in some respects ever-expanding database portfolio in cloud, so I think it's worthwhile to kind of step back for a second and look at how Cloud SQL fits into the overall picture. Leftmost on the slide, you see our BigQuery product, which is our data warehousing product. We have object storage, which we call Google Cloud Storage. It's a great place to put files, blobs. It scales extremely well. In our non-relational area of the portfolio, we have Cloud Bigtable, which offers an HStore interface. And we also have Cloud Data Store, which is really mobile and web friendly. And we also find that especially folks building large games tend to use Data Store for things like user profiles and game stats because of its scaling. In the relational area of our portfolio, I'm going to talk at length today about Cloud SQL, but I also want to make you aware of Cloud Spanner. Spanner just went public beta in February. Spanner has been used for many years internally to Google. It is globally consistent and automatically shards data. It's able to scale out writes across many nodes. And that's one big difference between it and Cloud SQL, is that Cloud SQL, as I'll talk about today, is able to scale out reads. We can do read replicas, for example, to offload reads of a master instance. It does not scale out writes past a single node. So if you have a workload that is demanding enough that you need more than the write throughput of a single node, think of a VM here, then take a look at Spanner. Again, with the automatic sharding and that write scale out, it provides some really interesting options. Thing to note about Cloud Spanner and SQL is that SQL is really geared to offering industry standard compatibility. Again, we're offering vanilla MySQL, vanilla Postgres. Spanner is its own SQL dialect. It comes with its own set of compatibility. So as you kind of gauge those two services, note that those are some key differences. And then lastly on this slide, our in-memory product is App Engine Memcache. That's Memcache for our App Engine platform. And if you're not familiar with App Engine is a platform where you can run an application without worrying about the underlying operating system and without worrying about scaling the application. A lot of that's done for you. So generally, the question I get when I show the portfolio slide is, that's great. That's nice to see that breadth. But what do I pick? What do I choose here? And so we have a flow chart, and we have this documented as well online. The gist today is that we are looking at Cloud SQL in the bottom left-hand corner, which means we're talking about structured data that's largely not an analytical workload. It's relational, of course. And then this last question is, do we need horizontal scalability? And where this is really talking about, do we need horizontal write scalability? And if we are looking for compatibility and are satisfied with read scale out, not write scale out, Cloud SQL is the right pick from the database portfolio. Okay, next up, quick question for you all. Who in here is self-managing, managing yourself, a database like MySQL or Postgres or commercial database? All right, so most everybody. And anyone in here using a managed database service like Cloud SQL or Amazon RDS or Azure SQL or Heroku? So, and then we've got a kind of a mix. Looks like some folks doing both. Great. Okay, so let's talk a little bit about trade-offs, self-managed versus managed. Obviously, I have a bias. I'm a product manager for Cloud SQL. That said, I think like anything in technology, the decision to self-manage a database or to manage one, or to let a service manage one, it comes down to trade-offs. You are making trade-offs every day as you look at your technology stack. In some areas, you say, I want to customize this piece of technology or exert some level of control over it, and that to me is worth managing it myself, spending some extra time on it. Other pieces of your stack, you may say, I'm not willing to spend that amount of time on it, and thus I'll give up some customization, that piece of the stack. I think the difference between self-managing a database and going to a managed service is very much the same, where you're going to decide, potentially on a per database basis, this is a database I want someone else to manage for me. I'll live with less customization. This is one that I must customize for some reason or want to exert more control over. When I think about self-managing a database, versus going to a managed service, it starts with the infrastructure. If you are running servers on premise and to anyone in the room managing their IT environment, hardware and all. Nope, great. Okay, even if you're not, then I'll kind of accelerate through this part. Even if you're using a cloud provider, a colo, someone that's taken care of racking and stacking servers, et cetera, take a look at how server maintenance is handled. And I say that because these servers still exist, whether we're managing them or not. They've got power supplies that can fail. They've got NICs that can fail. Know how your vendor is handling those type of failures. If you look at Google Cloud Platform, our VM stack is called Compute Engine. Compute Engine uses a technology called live migration to migrate your VM away from a server with some sort of hardware issue potentially to another server. And it does that without downtime. We take advantage of that in Cloud SQL as well. Take a look at how your vendor handles a power supply failure, a NIC failure, et cetera, because that matters in a big way to your databases. As we go up the stack, this gets fairly obvious. If you are self-managing a database, you're installing the operating system, you're patching and updating the operating system. With a managed service, you don't have access to the operating system. In Cloud SQL, you don't know what kernel we're running. We don't allow SSH access. You don't even know what operating system is underlying the database. Similarly, for the database itself, in the self-managed world, you are doing the installation, you're handling the updates, you're doing the backups. In a managed world, you're not doing the installation, you simply provision an instance, which we'll see in our demo. You are not handling the patches and updates as well, and we'll talk about how those get handled. And backups are generally made automatic or very easy for you. Lastly, in terms of some advanced functionality, high availability we'll start with. If you're self-managing now, you are picking a replication technology. You are setting up some sort of health monitoring of your master and maybe your failover instances, and you're deciding, do I want an alert that pages me and I trigger a manual failover, or do I want to automate this using scripting or something along those lines? So you're managing that high availability. The other thing I'll note is that this differs greatly from a managed service where managed, all those things I just described, are kind of taken care of for you. The replication is done on your behalf. There's built-in status monitoring and will trigger failovers, for example, without you even having to be aware of it. The thing about availability with self-managed and managed is just beyond the technology is you're backed by a team when you go to a managed service. At Google, that's our SRE team. This is a team that monitors database instances 24/7. When something goes wrong, there is a human looking at these instances or a set of instances. When you're self-managing, you're taking that responsibility yourself. You're going to get paged, or you're going to be the one who, at 3 a.m. potentially, is solving an issue. Lastly, we tend to forget about monitoring, and I won't get into monitoring in any deep way here, but what I'll note is this is more than just, am I collecting my SQL error logs and slow query logs? It's more about, can I easily get those logs to a third-party utility like Splunk? And a managed service will take care of that plumbing for you. For example, Cloud SQL can post your logs pretty easily to PubSub, which has a tie-in to Splunk as an example. When you're in the self-managed world, you're doing that plumbing yourself. You need to figure out how to get those logs to something else that you want to consume them with. So hopefully that gives you a kind of a fair rundown on this managed versus self-managed question. I hope it answers some of what Cloud SQL does as well. But the best way really to see what Cloud SQL does is to see it in action. So let's take a quick look at the product itself. I'm going to create an instance. I've created a Google Cloud project called Percona Live conveniently. Let me create an instance today. I'm going to create a MySQL instance, but I am happy to note that Cloud SQL supports Postgres as of last month in addition to MySQL. So if you're looking for managed Postgres, Cloud SQL has that in beta right now. When I was here last year at Percona, we had just announced Cloud SQL second generation, our latest Cloud SQL platform. It was beta at the time. It went GA in August of last year. It's really been popular with our customers because it offers a lot more performance than our past platform had. So we'll create an instance on second generation for MySQL. As I walk through this, we'll call this instance Percona Live DB. I will take the default version here, which is MySQL 5.7. We also support 5.6, and we'll be looking forward to supporting MySQL 8 when it's ready to go from Oracle. Your first choice here is where in the world do you want to put this database. Google offers 5 regions right now. We actually have a pretty aggressive schedule to offer many more regions this year. If you're interested in that, talk to me after the session here, or we posted it online with a global map that shows you where you can land these things in the future. For now, I will pick, let's do this in Asia. So we will put this database in Taiwan. And one thing to note here, if you're running an application also in Google Cloud, let's say you're running a VM, or maybe in our container engine platform, you're running Kubernetes. Actually, I'll go get more specific. If you're running a VM and you've placed it in Asia East in this particular zone, I recommend that you create your master Cloud SQL instance in the same zone. Your latency, network latency is best within the zone, higher latency outside of zones, or between 2 zones. And I'll note that for Google, a region means just a geographic location where we have multiple failure domains, where we have multiple data centers. You can think of this. Our zones here represent those failure domains or those data centers. So when I talk about regions versus zones, I'm picking a region in the world, and within that region, we generally have 3 or more failure domains, 3 or more data centers, and I'm picking a specific data center to put my master instance in, which in this case, I'll pick B, because that's where my application resides as well, and I want the lowest latency I can. All right, next choice here is machine type. Google Cloud SQL runs on VMs. We run on compute engine VMs, just like you could spin up yourself. As part of those VMs, you choose how much resources you have with respect to CPUs and memory. So Google Cloud SQL offers a pretty wide variety of machine types, from development-focused instances way down to below a single CPU core and about 600 megabytes of RAM, all the way up to 32 cores with more than 200 gigabytes of RAM. What I'll note here is that all of these instances will allow the same feature set on Cloud SQL. You can do failovers, you can do point-in-time recovery, et cetera, et cetera. However, the shared core instances are really meant for development. In fact, we don't offer an SLA on those shared core instances. If you want an SLA, if you want to really run in production and get the full backing of Google, you need to be looking at the standard or high memory machine types. So for today, let's pick a high memory machine type. The thing I'll note to you all is if you are looking to run a production workload, most of our customers find that they can save a bit of money by going to the high memory shapes. We tend to see MySQL workloads especially more heavily utilizing RAM than CPU cores. So I'd recommend taking a look at the high mem instance types. So I'll start with a 4-core, 26 gigabyte memory instance type. Select that. My next decision is around storage type. We offer SSD and HDD, where obviously SSD is much faster. The thing to note about Google Storage is that Google Storage performance scales with capacity. And this is not quite as intuitive as I think if you're coming from an on-prem world. So Google Cloud SQL's form here includes a performance calculator. We basically have 2 variables when we think about performance and storage performance. The size of your SSD disk dictates how many IOPS we're able to provide for you. And there's a cap based on the number of CPU cores that you choose. So in this case, I picked an instance type that has 4 CPU cores. What that means is I have a maximum IOP capacity of about 10,000 for writes here. the thing to note is that my performance calculator is telling me with a 20 gigabyte SSD, I'm only able to deliver about 600 IOPS. So one thing I'll recommend is balance your performance. If you're choosing a 4-core VM, consider ratcheting up the capacity of your SSD because you want to get the IOPS that machine can deliver. So in this case, let me ratchet this up a bit. We'll add a 0 here. You can see that the calculator starts to adjust. I'm going to increase it just a bit more here. Let's go up to just 400. And now we've effectively maxed out the capacity I have from this machine type. If I wanted to go further, I can go back and change this selection. Let's go way up. Let's go to a 32-core machine, our largest machine type right now. And what you'll find is now I can go up to a maximum of 25,000 IOPS. The IOPS numbers, the number of CPU cores, no secret, they're going to keep going up. These are larger numbers than I showed last year. I'm sure when I'm here next year, there'll be larger numbers still. What I'll always be recommending is balance your performance. So again, here, I would not recommend this configuration because I'm not taking full advantage of the IOPS this machine can deliver. So let me ratchet this up a bit more, and let's start to max out these IOPS. So now we're getting close. So we'll call this good for now. But again, you're scaling storage IOPS with capacity, and they're limited by CPU cores. The reason we include this performance calculator is, frankly, we don't expect you to remember any of the formulas that go into this. I'll show you some of these in the slides. The calculator's built in. Just make sure you're balancing these things as you go. I'm going to talk about our automatic storage increase feature a bit more in detail as we get into the slides. But what I'll note here is that when you enable automatic storage increase, you tell Cloud SQL, take a look at how I'm using my capacity about every 30 seconds. We look, and when you're getting close, and generally that means if you're getting within about 5 gigabytes of your maximum, we're going to automatically increase the storage capacity, which increases your IOPS. And we're going to do that online, so it does not affect your database running. I will note that I strongly encourage everyone to use this feature because we monitor all of our databases on Cloud SQL, and inevitably we see alerts, customers who run out of disk space and who take an availability hit because they ran out of disk space. It's just tough to see because it's an avoidable issue, especially where you can check a box and kind of let us take care of it for you. All right, next up, backups and binary logging. Let's start with backups. Don't lose data, right, with databases. That's the number one rule. Automatic backups are pretty easy to schedule with Cloud SQL. You set a window, and these get taken every day. I'm going to set a window for, let's just say, tonight at 11 p.m. to 3 a.m. This tells Cloud SQL, take a daily backup for me. Make sure to do it in this window. We take disk-based backups, meaning we take snapshots at the block level. We aren't doing a MySQL dump, for example. This does allow us to take backups with very little performance overhead. In fact, we don't limit how many backups you can take in total because we're pretty confident in the way they cope with performance. And it allows us to take a backup that finishes every single time. So we don't have missed backups. Automatic backups give you a rolling 7 days of backups. So that means when I turn this feature on, I always have the last 7 days of backups. I'll also note that you have the option here, and again, it's on by default, and I recommend it, to enable binary logging. When you enable binary logging, we're now capturing in our backup both your data files and your binary logs, which means you are able to point-in-time recover. So we have 24-hour granularity on the backup itself. If that's not good enough for you, if you want to get to specific transactions, if you have some kind of event that you need to recover from, you can do so as long as binary logs are enabled, and then you can get to a specific transaction where things went awry in your database. The other thing we use binary logs for is failover. And I'll talk about this a bit more, but for this presentation, I'm going to enable failover. What this does is tell Cloud SQL, build a failover replica, monitor my master instance. If something goes wrong in zone B of Asia East where we're creating this, I'm going to fail over to another zone where I've created this failover replica. Cloud SQL will automatically create this replica in a different zone than zone B. We told Cloud SQL, put my master in zone B, so this replica is going to go in zone A or zone C or some other zone than B because it's a separate failure domain. Maintenance windows. I mentioned at the top that as part of a managed database service, we take care of things like updating MySQL, keeping your OS up to date and patched, et cetera. This does incur downtime when we do this kind of maintenance on a machine. So we allow you to set a maintenance window that tells us, let's say, only do maintenance on Saturdays from midnight to 1 a.m. Keep it out of my business hours, for example. And we also have a maintenance timing field here which allows you in your project, if I imagine I have a development database and I have a production database, I might put my development database on the earlier maintenance timing schedule, and I'll put my production database on the later maintenance timing schedule. What this does is tell Cloud SQL, separate the updates for these two databases by about a week. Try to update the development database first, maybe the first Saturday of the month, and my production database will get updated the second Saturday of the month. That gives me a chance to see the update occur, test my application against the latest updates before it hits production, for example. So in this case, we'll say it's a production database, and in this case, I want the later timing. Note that whether you pick earlier or later timing, you get the same updates. The earlier setting is not a beta setting. You're not getting bits and bytes that we aren't sending to the later maintenance timing. Okay, we'll set a very secure root password here. I think Percona will keep everyone out. And I won't bother right now setting flags or authorized networks. I will note Cloud SQL does offer a number of flags in case you are coming from a database where you've set some of these things and want to make sure that you've got certain flags customized for your application. So with that, I'll hit create. Oops. There we go. I'll hit create. The instance creation itself takes about 3 minutes. So while that's going on, let me switch back to some slides and we'll carry on. Okay, so just a couple features that we'll spotlight here. Go ahead, let's take a question.
Okay, so the format available feature, would that be any extra charge for using that?
So the question for the recording is, does automatic failover cost more? And you won't be surprised to learn that yes, it does. What we're doing in the background, and you'll see as I go back to the demo, is we're actually creating a separate MySQL installation for you. So it's a separate VM in another zone that happens to be using semi-synchronous replication from the master. What that means is you are doubling your charge. Rather than paying for a single instance, you're now paying for two. So you pay for, it's exactly double in that whatever storage your master is using, your replica will use as well. That answer your question? Great. Okay, let's spotlight a couple features here. Instance sizes I mentioned, and we just had a question about pricing. Usually when I show the variety of instance sizes, someone says, what kind of pricing does this look like? For the smallest instance type, which we call an F1 micro, one of our development instance types, the monthly charge is less than $10. It's right around $8 a month. So if you're looking just to get started and want to kind of explore Cloud SQL, it's a good way to go. We always, of course, recommend for production applications, or if you're wanting to get serious about any sort of performance with MySQL, pick from our standard and our high memory instances, which are, of course, more expensive, but also come with many more resources. Again, the shared core instances are really just kind of for development and test. Looking at storage, and hopefully I've hammered this point home enough, storage performance is tied to capacity. So size your performance first, and then worry about how much disk you're going to use. When we look at the automatic storage increase feature, we had a customer called Descartes Labs, who is using our Cloud SQL for Postgres product. They sent this screenshot. They were importing an XML file that contained OpenStreetMaps. It's about a 50 gigabyte XML file compressed. XML is pretty verbose as a format, so it compresses well. And Tim at Descartes said, I wonder how large this will be when I import it in a Postgres instance. It's 50 gigabytes compressed XML. How big is that going to be in Postgres? And I will note, Descartes is a really savvy company when it comes to geospatial applications and Postgres, but he still had to guess. So he's running a VM, happened to be on Google Cloud, but he said, I'm going to install Postgres myself. I'm going to make a VM with a disk of around 250 gigabytes. I'll just go 5x what this compressed XML file is. He starts importing it. A couple hours later, he gets this error. He's out of disk space on the VM. And so he says, okay, I can either increase my disk space, kind of reformat my file system and kick this off again, or I'll go ahead and try Cloud SQL for Postgres. He does that, kicks this off at 3 p.m. with auto storage increase on, and he sends us this chart the next day. So you can see he starts this import at 3 p.m. This chart is built into Cloud SQL, shows how much disk space is used. We started around, this is right around 10 gigabytes, our default. And then Tim's instance grows up to, I believe it's around 387 or so gigabytes over the next few hours. So he kicked this off, did some other things in the office, went home, checked it that night, and around 9 p.m. the import had finished, and that's what it ended up at. And he wrote us an email saying, thanks, I didn't have to figure out how to resize the disk, and more than that, he's at a startup where they want to get their costs right. So he said, I wasn't sure how big this data set would be. Now I know, and I'm paying for 387, whatever that is, gigabytes of space because AutoGrow keeps my disk capacity pretty close to what I'm actually using. So in his case, it worked out really well. Again, I recommend you turning it on because it just saves you a headache of running out of disk space and taking an outage. One thing to note here, I've been talking a lot about how storage capacity influences performance. Tim, I think, just wanted to see how well AutoGrow worked, so he started with the smallest disk size. He knew his import was going to at least be 250 gigs. And you can see what happens with respect to performance in this chart. Tim starts at pretty low import performance because he's on our smallest disk, so he's getting our fewest number of IOPS. As the disk grows, you can kind of see these inflection points in the graph where not only is the capacity growing, but the IOPS go up. And so Tim now is getting much better performance because we're delivering more IOPS, and probably here he really starts to move and go forward. So if you know roughly how much space you're going to use, I always recommend just size the disk for it because we're going to deliver the IOPS straight away. Tim could have probably finished this faster if he had done that, but I think he was just checking out the feature itself. In this case, a good guess would be 250 gigabytes since he knew he'd already maxed that on his VM. It's definitely going to be that, and in this case, it ended up being closer to 400. Last note on backups here. I talked about backups and maintenance. One thing about backups, we take automatic backups, rolling 7 days, we clean them up for you. When day 7 turns into day 8, we delete that backup. So you always have 7 days of backups, inclusive of binary logs if you turned them on, which means for the last week, I can get to any position in my binary log that I want. If you want to take backups of your own accord, of course you can do that through the UI, through the API, through our CLI. Backups you take on your own, we call on-demand, you might call manual backups. You keep those as long as you want. You manage them. So if you want to keep those backups for 2 years, that's great. You can keep them as long as you like. We won't destroy them ever. You have to delete them yourselves. The other thing I'll note in the demo that I showed you is that our UI is built on top of our public API. So if you're a developer and you're thinking, I wonder if I can do that through the API, the answer is yes. If you're seeing it in the UI, you can get to it from the API. We build on top of the API for that reason. Okay, let's talk a little bit about performance, and I'll start with infrastructure. Scaling up is always kind of the most intuitive thing. I showed you how to select number of CPUs and RAM based on the machine type that I picked. You can always change those on the Cloud SQL instance. The thing I'll note here is that when you change those, you do incur downtime. We have to reboot the VM. We put you on a different VM, which means you're down for about 3 minutes. So if you want to change RAM, CPU, you're going to take about 3 minutes down. When you want to change storage performance, if you're adding more capacity, for example, again, that's always an online operation. You don't have to take your database down. I promised I'd show you our formula for storage performance, which is roughly for every gigabyte of storage I add, SSD storage that is, I get about 30 more IOPS. Don't bother remembering it. That's why we have a performance calculator in the product itself. These numbers are also going to be stale in the near future because they keep going up. Okay, at some point, I'm sure all of you have said, it's nice to run on one big database, but I've got a workload now that's demanding I scale out at least my reads. If you want to do that in Cloud SQL, it's fairly quick to do. We do offer read replicas. You saw kind of what the UI looks like. We can quickly add one or more read replicas to the master Percona instance that I created. And then we can begin pointing our applications at those read replicas. Really common use case for this is I have an analyst team or a reporter who runs reports, large queries on Fridays or on Thursdays. It's really nice not to throw those at my master instance while it's coping with writes and so forth. In those cases, read replicas are great, and you can point application reads at those read replicas without bothering your master instance. 2 other things to note here. The first is that we use semi-synchronous MySQL replication between master instance and the failover replica. That guarantees or aims to guarantee that we never lose data on a failover. We don't ack a commit on the master until the failover replica has it. This differs when it comes to read replicas where we use asynchronous replication. We're doing that because we don't want a read replica to hinder the performance on the master. And generally, a read replica will never fail over to, so we are a little less worried about it being exactly in step transaction-wise with the master. What this means in practice for you is that if your read replica is falling behind when you're running these reports, it could be some number of transactions or seconds behind the master. Okay, so we've talked about performance from an infrastructure perspective. Let's quickly talk about database level tuning. And I'm not going to go into real deep InnoDB tuning here, but what I'll note is that Cloud SQL aims to give users a good out-of-the-box experience on our compute engine VMs and our what we call persistent disk, our persistent disk layer. What we do is a set of tuning for every single Cloud SQL instance that we think does a good job of leveraging the strengths of compute engine VMs and of persistent disk. So if you are interested in kind of what can happen when you look at tuning, or when we start tuning, we took a workflow of around 128 cores, and we looked at transactions per second and variability of those transactions per second. What you see here is pretty wide variability before tuning. What we found in this case was that tuning dirty page flushes in InnoDB made a big difference in that variability, and you see the tuned results on the left. There are a number of InnoDB tuning parameters that we've explored and have optimized in Cloud SQL. So generally, you'll say, okay, great, what are they? We post those publicly. So if you're coming to Google Cloud, whether you want to use Cloud SQL or not, I encourage you to take a look at these. If you're going to run MySQL on Compute Engine and use PD, start with our tuning. And then from there, you can further tune for your application workload. If you're on Cloud SQL or going to Cloud SQL, know that this is done for you. And if you're curious, you can take a look at what we've done. Expect these to change. Performance is never ending. I'm sure our tuning will never be ending, but we're going to be updating our tuning on this URL. And lastly, we'll kind of round this out with connecting Cloud SQL, because it offers vanilla Postgres and vanilla MySQL, means you can use standard connectors to get to MySQL and to Postgres. I note here that we've got connectivity from kind of our major application platforms in Google Cloud, our VMs, our container engine with Kubernetes, and our platform as a service app engine, both standard and flex environments. If you're coming in from public connections outside of Google Cloud, hopefully encrypted with SSL, we use native connectors, as I mentioned, and I think there's one other item here that's worth some note, and that's the Cloud SQL proxy. So we'll dedicate just a little time to talking about the proxy. Cloud SQL proxy is a client agent that you can install, for example, on your laptop. It installs on Windows, Mac, Linux, etc. So if you put this on your Mac laptop right now, it will automatically encrypt the connection to Cloud SQL. And it's great when you have a device like a laptop that is usually coming in from like a dynamic IP address. So if you connect to your Cloud SQL instance from Percona Live, and then 2 hours from now from a nearby Starbucks, the proxy will handle what you otherwise would have to handle through some firewalling, right? Because you probably don't want to allow any connection to a database from any random Starbucks. Normally, you'd handle that through firewalling. The proxy uses an identity, or what we call a service account, to authenticate that connection and at least allow the connection to your database. What this means is you don't have to make firewall settings to connect from Percona Live or from the Starbucks 2 hours from now. So if you've got developers connecting to databases, especially from devices like a laptop, this is a really convenient mechanism. The other thing it does, and I've shown a little bit of what this looks like at the command line here, the Cloud SQL proxy makes your cloud database look local. So what you see here is I'm on a Mac or Linux, some kind of Unix-style client, and I run the Cloud SQL proxy. You can see that I've got my Percona Live project and my Percona Live DB in Asia East. And when I run that, then I can use my standard MySQL client. I can point it at a socket which looks local. So I've got a Cloud SQL directory on my laptop. And to this MySQL client, whether this is MySQL Workbench client, my Python app, this looks like a local database. I connect with that same connection string, whether I'm at Percona Live, whether I'm in Starbucks, whether I'm back at my office, and that connection string stays the same. For clients that don't support Unix domain sockets, you can specify a TCP socket. And I mention that because then it's really clear. We're using a loopback address here. This is a cloud database somewhere in Google's Asia East data center, and I'm connecting to it with a loopback address. So this looks local then on your laptop or wherever you install the proxy. Usually people ask me, are a lot of people using the proxy? Can I trust it for connectivity? The answer is yes and yes. We actually use the proxy for connectivity from App Engine Flex and from Container Engine. So we put a lot of production traffic even from within Google Cloud to handle dynamic IP addresses. If you're not aware of Cloud SQL Proxy, I think there's some great convenience with it, and especially if you're coming in from a client with dynamic IP addresses, I'd encourage you to check it out. It makes a cloud database look local. Okay, let's wrap up here. Just a couple next steps. So hopefully the presentation is put together that Cloud SQL really is aiming to make management less painful. We're trying to take away the mundane. What you didn't hear me talk about was how we optimize queries or help you design schemas. We don't do that. We're not a DBA replacement. But for DBAs out there, hopefully, we're getting them to be able to focus on some things that are a bit more interesting than patching a database and keeping an OS up to date. Golden rule, never lose data. Make sure your backups are running at least every day and are finishing every time. We can guarantee that with our disk level backups. And of course, if you want to keep backups for a long time, you're welcome to do so. Scale performance, we do that with infrastructure. We also do some tuning of InnoDB parameters on your behalf. You can find those online at that URL that I mentioned. And we do expose a number of Cloud SQL flags if you want to do some of your own tuning. And then lastly, connect and get started. I talked about the proxy, talked about native connections. Getting started is pretty easy. If you haven't already created a Google Cloud account, please do so. You'll get $300 worth of credits. That goes a fairly long way on some of our smaller Cloud SQL instances, and I encourage you to get to know it yourselves. With that, I want to thank you for joining me on the third day in the afternoon when we're all fatigued at this conference, and I'll open it up to any more questions you have. Thanks.
I totally get the value of a managed database. But in my mind, it's a question of like who, and how would you compare, what you're offering versus AWS RDS? Is it certain features? Is it performance? Is it something else?
Great. Yeah. So the question is, when you feel like yes, managed database is right for me, how do I pick? Who do I want to go with? Generally, what I see is it's first and foremost kind of a platform decision. Databases never are turned up alone. So most of our customers come to us and want to understand our managed database service, Cloud SQL, but also want to understand our Kubernetes implementation or how Container Engine works. They're looking to put together a solution. So that's usually the starting point. If I were to compare Cloud SQL against competitors, I think what Cloud SQL is really trying to do is first and foremost compatibility. We're not offering a compatibility layer. We are really trying to be vanilla MySQL, vanilla Postgres. And that's important because you can expect us to keep up with the latest versions of MySQL and Postgres. I can't guarantee that when MySQL 8 goes GA, we'll be there immediately, but I can guarantee we're going to be there pretty quickly afterward. And I think as you look at managed database services, the more a service changes the database they're offering, the less likely you are to get at least latest version compatibility, if not some other pieces of compatibility. All right, if there are no other questions, I will leave you to your next session. Actually, we got one more.
How about the monitoring feature that, monitoring stuff that can it be also used for?
Good question. So the question is, can I use other monitoring tools on Cloud SQL? As a starting point, Google Cloud always recommends taking a look at Stackdriver, which is our built-in monitoring for all of Google Cloud. When it comes to other monitoring tools, one of the things you'll see Cloud SQL do in the near future is give access to the MySQL performance schema. And so if you've got a monitoring tool that can read the performance schema, then indeed you can use whatever tool you like. The other thing we do offer via Stackdriver is an API where we export metrics. So if you're using a third-party tool, maybe Datadog, et cetera, you can go query that API. Great questions. Thanks, everyone, again.